Alright guys, I'm going to try to do this as best as I can. As you can tell, I do not have a voice, so just bear with me. So going over this document, we need to understand what proteins, carbohydrates, and fats do. A protein is a type of macromolecule that can be found in your body that is going to be used for growth and probably more importantly, repairing damaged cells. So as you're going through your normal day-to-day functions, you have to be able to repair the tissues that you have damaged, and proteins are going to be able to do that. Now, if we take a look at the carbohydrates, I want you to immediately think as quick energy. They are used for quick energy. This is your energy molecule. This is the type of macromolecule that you take into your body when you eat that is going to give you the energy to get through the day. So as we see for this next part, again, proteins, growth and repair. And then for the last one, fats. Fats are going to be a little bit interesting because fats actually have a lot of different functions. Fats have the ability for energy storage. So, energy storage, this is when your body doesn't use all its energy that it needs. It's going to store it in the form of fat. And it can also be used as insulation, where it's going to keep you warm. And then finally, it can also be used for communication in the form of hormones within your body. So your hormones are the ways that your cells can kind of intercommunicate with each other, and they're going to be made out of your fats. So when we take a look at what the purposes of these are, proteins are for growth and repairing damaged cells, carbohydrates are for that energy, and fats are for that energy storage, insulation, communication in the form of hormones. Now, as we continue to work our way down, we see that we have an image of all three of the carbohydrate, the lipid, and the protein. Now, one thing that we can notice is that the carbohydrate has these carbon atoms that are attached in the center, and they're completely surrounded by a lot of hydrogens and oxygens. If we take a look at the lipid, we see a longer chain because, again, we're actually storing more energy with a lot of hydrogens and oxygens again. Now, one thing that I want to note that is really different is if we look at the protein, we have this element right here. This element is nitrogen. And I need you guys to make note and understand nitrogen is our key difference that only protein, in this case, is going to have. So when we are taking an assessment, when we are taking a look at our lab on Monday, if you test positive for nitrogen, you are automatically a protein. So what we can identify here is that based off of this key, the elements that we're made out of is carbon, hydrogen, and oxygen. Lipids are also made out of carbon, hydrogen, and oxygen. And then proteins also have carbon, hydrogen, and oxygen. But more importantly, again, it has that nitrogen. Nitrogen is your key to understanding that it's a protein. Okay? So, some of the similarities that we could list. There are many different things that you could list here, and it could all be working fine for me. I could see you saying things like it's all made out of carbon. I could see you say something like it all has hydrogen, and it all has oxygen. We could also see that we have this backbone of carbon. It's just that the chains of them are different lengths. Okay. Now, for some differences that we can note, is that we see for the lipid specifically, it is a very long carbon chain that contains high amounts of energy. The glucose, or the carbohydrate, is a short chain that has moderate energy and is used for quick energy. This is going to get you the energy through the day. And then for the final one, the proteins have nitrogen and short carbon chains. This is for growth and repair. For later on, we're going to talk about how in your body, if you are out of your lipids and you're out of carbohydrates, you can actually use this as a last source of energy too. So, if we take a look at this description here, the main thing that we have to keep in mind is that the more carbon atoms that you have, the more energy you're going to be able to get out of it. So using this information from Model 1, is a carbohydrate, a lipid, or a protein more likely to be a good source of energy for an organism? Now for this, I'm going to say that it could actually be two things. Carbohydrates are much better for short term, okay? This is going to be if you're going to be running a race, they tell you to load up on your carbohydrates to give you the energy to get through that race. Your lipids, though, are much better for long-term energy. This is going to be like just sustaining life for a long period of time, okay? Now, while your lipids are being stored, okay, your energy is stored. This is like a backup if your body absolutely needs it. So for this, I'm going to say that your carbohydrate is better for immediate energy. Your lipids are for storing. So if we're talking about trying to get a good source of energy and food that you're going to eat, you want this carbohydrate because it's going to provide that immediate, quick energy that you need. Okay? Now, in this next model, we're taking a look at the elephant's diet, who is taking in sucrose, which is sugar, and it's adding water to this, and it's breaking it down to create glucose and fructose. What we refer to this as is a chemical reaction. Anything that is onto the left side of this arrow are going to be your reactants. So we see that for the reactants for this, we have sucrose and we have H2O, which is just water. Now, your sucrose and your glucose are going to work together and they're going to break apart this bond that exists right here, and it turns it back into its original source of glucose as a product and fructose. Now, one thing that I want to make note is that sucrose is what we call a disaccharide. Now, when we say di is a fancy word that means two. Saccharide is a fancy word that means sugar. This is a two sugar ring, okay? Whereas if we take a look at glucose and fructose, they're what we call monosaccharides. Okay? Mono means one. Saccharide, sugar. They're a one ring of sugar. So if we're trying to identify who is more complex, we're going to say that it is our sucrose that is the more complex because it is that disaccharide. So we're going to say sucrose. Because it is a disaccharide consisting of 2 sugar rings. Now, when we see with this elephant, when this bond is broken, you do get a little bit of energy. Not a lot, just a little. But the main things I want you to get from this reaction is that you get glucose and fructose. These are your products. So after it has digested that sugar, it's getting glucose and fructose. Now for the next part, it says that starch is a complex carbohydrate that is found in plants, which contains approximately 200 glucose molecules. Now glucose, being that monosaccharide, can also be classified as a carbohydrate. Essentially what we're having here is that we are storing glucose molecules which means that we are storing carbs, and as an energy storage, starch is energy storage. I want you guys to make this note for me. Not only is it energy storage, if lipids, which are fats, are to humans, then we can say that starch is to plants. And what I mean by that is that your fat stores the energy in your body. Starch is that version for plants. This is the energy storage molecule for our plants. Now building on that, we have our Model 3. In Model 3, we're taking a look at what is called a dipeptide. Again, di meaning two, peptide is talking about how we have 2 amino acids. This one is taking a look at the amino acids that are going to be used for making proteins. Now, one thing to make note is that in your body, you have 20 different amino acids that you have to have in order to make thousands of different proteins. Now, you can have those 20 different amino acids being used in many different varieties and many different forms that are going to make all of the proteins that you need for survival. The only problem with this is that your body only can produce 12 of them, meaning that the other 8 comes from the food that you consume. Okay? So what's happening here is that you are taking in a dipeptide, you are taking in a protein from another thing. As you consume it, you are reacting with water, which breaks it down into the original amino acids. This is how you get that other 8. Your body is consuming proteins that then break it down, freeing up those amino acids that you can then use to make your own proteins. Now I'm going to come back to this in just a second, but that's where we get down to here. Okay? It is not a primary energy source. That's important to note. Proteins are not for energy. Instead, they are used for growth and repair. Okay? However, it says that this dipeptide is breaking down into 2 amino acids. Why is this necessary? It is necessary to break down the dipeptide because we need to free up the amino acid so that our body can use the amino acids to make our own proteins. So we're taking in that dipeptide through the food that we consume, we're breaking it apart, and we're using those amino acids that are freed up to make our own proteins. Now jumping back up to here, we can see that for our amino acids, they all start off exactly the same. Notice how up at the top, we have this amino group, we have this carboxyl group, and it's exactly the same. It's the same for every single amino acid. Where we start to see differences is down at the bottom. These differences is what we refer to as the R variable group. And it's a variable group because these are different. All right, so this here is what we're going to circle for the R group. This here is the R group. This here is the R group. And this here is the R group. Now I want to make note about how we can identify amino versus the carboxyl. The amino group has nitrogen. The carboxyl has carbon double bonded to oxygen. So if you are trying to identify the amino group, look for nitrogen. And if you're trying to identify the carboxyl group, look for carbon that is double bonded. It has 2 lines to an oxygen atom. Now, as we move into our next model here, we're taking a look at this lipid. Now, this lipid here is what we refer to as a triglyceride. We have this backbone of a glycerol that is connected to a bunch of carbon atoms, which is what these little squiggly lines are supposed to represent. These little squiggly lines are what we refer to as a fatty acid. So it says because of monoglyceride, molecules have more carbon atoms than glucose molecules. What can you refer about the energy available on each atom? The energy available is higher. The more carbon you have, the more energy you can get. Okay? So because as we look at this, each of these points on this squiggly line represents a carbon atom. Because there are so many carbon atoms, there's so much energy that we can get out of this. And again, if we look back at this building block of this lipid, lots of carbon. Little carbon, lots of carbons. Now the lipid again is just for energy storage, and it's going to be used if you do not have carbohydrates in your body. It's kind of like your body's main way of making sure that it has the energy that it needs for survival. So the energy available is higher because the more carbon atoms that you have, the more energy that you can get. Now in our last case scenario, we are taking a look at what happens when those carbons are going into your cells. In this case, this organelle right here, a mini organ-like structure in your cells, is what we refer to as mitochondria. I want you to make note, I'm going to let you guys do the summary, but mitochondria is the powerhouse of the cell. In other words, the mitochondria are going to convert your glucose into ATP energy. ATP energy is the energy that your cells can then use to do their cellular functions and are for survival. They absolutely need this ATP energy. So what's happening in this model is that my glucose, represented by this carbon bonded to carbon, is going into the mitochondria. It's being converted into ATP energy. So it says, observe the cell model above, explain what is happening with the carbon-carbon bonds. The carbon bonds are breaking to release chemical energy. This is going to go into a reaction that we're going to talk about later called cellular respiration to create ATP energy. So carbon bonds are breaking into to release chemical energy that are going to go into a chemical reaction called cellular respiration that is going to result in ATP energy. And ATP energy is going to be used by the cell for cellular, sorry for the misspellings, functions. Okay, they need this ATP for survival. Now, in our last case here, this is that we want to look at the molecules above. We want to circle each bond between carbons only between the carbons. And we want to count up how many there are. That's going to be this, 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 and this, but not these. We are looking specifically between carbon and carbon bonding. So if we look at the glucose, there's 1, 2, 3, 4, 5. There are 5. If we look at the fatty acid or the lipid, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And if we look at the protein, there's only 1. Now, when we break apart those carbon bonds, that is what's going to be giving you the energy that you need to create that ATP energy. So, it says that for each of these bonds that are broken, you are going to produce approximately 347 kilojoules of energy, which means that for my carbohydrate, I have 5 bonds that are going to be breaking. I'm going to be multiplying that by the 347 kilojoules of energy that I'm going to be getting. And when I do that, give me just a moment, I'm going to pull up my calculator. 5 times 347 is going to result in 1,735 kilojoules of energy. For the lipid, we have 11 times 347, which is going to create 3,817 kilojoules of energy. Whereas for the amino acid, we only have 1 times that 347, which is only going to create 347 kilojoules of energy. This is the reason why we say that proteins is not a source of energy for your body. This is a last case scenario. As a matter of fact, what your body is going to do is it's going to rely on the carbohydrates that it has to get the energy that it needs to go throughout the day. Any energy or any carbohydrates that it does not use will get stored up in the form of a lipid. And this is going to be used as a storage. This is going to be if your carbohydrates are not in your body is then going to turn to its lipids, its fat reservoirs, to then get the energy that it needs. And in the final case scenario, if it's out of the lipids, it's then going to turn into your proteins. It's going to turn to your proteins. This is the reason why if you have somebody who is basically starving, where they're not eating, they don't have the carbohydrates because they're not taking in food, so their body is going to turn to their fat. As soon as their fat is gone, this is when you start to see their muscles start to atrophy, or their muscles start to decay, okay? Because it needs energy for survival, so it's going to turn to the proteins. Your proteins are not a main source. Your proteins are supposed to be repairing that damaged tissue, but if absolutely necessary to keep for survival, it will use it, but it's not meant to, okay? Your carbohydrates are your main source of quick energy. Your lipids are for storing extra carbs in the form of fat, and this can be used for energy, like if you don't have the carbohydrates, whereas your proteins are for growth and repair, not energy, unless it absolutely has to, okay? But I want you to keep in mind, growth and repair, that is your main idea. So it says, based on your calculations, which 3 molecules have the most potential energy? Which of the 3? The most potential energy is your lipid. What is the function of this macromolecule? The function of this macromolecule is energy storage. This is because we are converting extra glucose into fat to be used later. Okay? And again, we can see that because I've taken my carbon and I've just created a long chain of it. Literally, I'm taking my carbohydrates, I'm turning them into fatty acids by connecting a bunch of them, and I'm storing it for later use. All right, so that takes me to the end of explaining what each of these are supposed to do. I need you guys to please make sure that you are making corrections if you need to. We are going to be taking an open note unit assessment in the next week, and this is a document that can definitely help you. If you have additional questions, please feel free to email me and let me know. I'll be more than happy to help you with what I can. I hope you guys have a great rest of your day, and I apologize for being this sick. As you can tell, my voice is totally gone. Have a great rest of your day.